Hello students, today in this session we are going to discuss about the transfer function of any electrical system. So during the lecture we will discuss about the basic elements of any electrical circuit, what is the transfer function and how we can estimate the transfer function of any given electrical network. So the basic elements of any electrical circuits are resistance, inductor and capacitor. The resistance governing equation is, if we want to calculate the voltage across the resistance, we can calculate it as VR, that is the voltage across the resistance, is equal to current flowing through the resistance multiplied by the resistance. Similarly, for inductor, the voltage across the inductor is defined as inductance multiplied by the rate of change of current flowing across the inductor. For the capacitor, the voltage across the capacitor is defined as 1 upon the capacitance value multiplied by integration of current flowing through the inductor. Or the current flowing through the inductor can also be defined as the value of capacitance multiplied by rate of change of voltage across the capacitor. To solve any electrical circuit, mostly we use two basic laws of Kirchhoff's. So the first Kirchhoff's law that we will use is for current, and the other Kirchhoff's law we will use for voltage. So we have two Kirchhoff's law, Kirchhoff's current law and Kirchhoff's voltage law. The Kirchhoff's current law states that the algebraic sum of current across any node is equal to 0. That means the incoming current across the node is equal to outgoing current from that particular node. So if we take example of parallel RLC circuit, so the total current will be equal to the current across the resistance plus current across the capacitance plus current across the inductor. And all these currents values can be replaced by their individual current with respect to their individual voltages. And then if we want, we can take the Laplace transform of that equation and calculate the current or the voltage as per our requirement. Similarly, for Kirchhoff's voltage law, we know that the voltage within that particular loop is equal to 0. So the algebraic sum of all the potential drops across that loop is equal to 0. So let's say if we have a series RLC circuit, so if we apply the Kirchhoff's voltage law, we will get the total voltage is equal to the summation of voltage across the resistance plus voltage across the inductor plus the voltage across the capacitor. And then again, as per our requirement, we can replace all these voltages with respect to their current values. And if we want, we can take the Laplace transform of those equations and calculate the desired voltage or current in the circuit. Next, we'll see what is the transfer function. So the transfer function of a system is defined as the Laplace transform of output divided by the Laplace transform of input, assuming zero initial condition. So what does it mean, zero initial condition? So zero initial condition means that whatever the energy storing elements, those are there in the circuit, that is resistance, inductance, and the capacitance. Out of these three, inductor and capacitor are only the energy storing element. So that means if we are saying zero initial condition, that means the energy stored in capacitance or in inductor will be equal to zero as soon as we are providing the power supply to that particular circuit. So this transfer function actually tells us that how the system transforms an input signal into the output signal. That is specifically in the frequency domain. And again, this transfer function is helpful in analyzing and designing the control system or any given electrical network. Now we'll take the example of RC circuit, that is series RC circuit. So here we are having two components, resistance and the capacitance connected in series. The total power supply is V in T. So first of all, to calculate the transfer function, we must know that what is the input and what is the output for this particular circuit. So for calculation, we are considering input voltage V in as input and voltage across the capacitor as output voltage. So we have to calculate the VC, that is the voltage across the capacitor, and V in, the ratio of VC and V in Laplace domain. That will be our transfer function. So simply we will first apply the KVL. So as soon as we apply the KVL, we will get that the total applied voltage V in is equal to voltage across the capacitor plus voltage across the resistance. We replace the value of voltage across the resistance with their respective resistance value and current flowing through that particular resistance. The current across the capacitor can be estimated as IT is equal to C, that is the value of capacitance, multiplied by rate of change of voltage across the capacitor. Now, if we replace this value in the KVL equation, we will get the equation as V in T is equal to RC, rate of change of voltage across the capacitor plus voltage across the capacitor. Now, if we take the Laplace transform of this equation, we will get the relation between the total voltage and the voltage across the capacitor in Laplace domain. And now simply we can take the ratio of voltage across the capacitor and total applied voltage in Laplace domain, and we will get the transfer function as 1 upon RCS plus 1. Again, here we should consider that the initial condition is 0. That means the voltage in capacitor is 0 at time t equal to 0. Now we'll take the another example of RC circuit. So rather than the capacitor component, now we are having the inductor in the circuit. So this is RL series circuit. In this we are having a resistance and a inductor. Again, to calculate the transfer function, we must identify that what is the input and what is the output. So for this particular example, we are taking input voltage as our input and the voltage across the inductor as a output. So the transfer function that we have to calculate will be VL divided by V in. Now if we apply the KVL in the circuit, we will get total voltage is equal to VL multiply VL summation of VR. And then we can replace those values with their respective component value and the current. So voltage across the inductor, we can define it as VL is equal to inductor multiplied by rate of change of current. If we take the Laplace of these two equations, we will get the same relation in Laplace domain or in frequency domain. Now, the value of current in Laplace domain can be estimated as V in divided by R into plus Ls. And that value can be replaced in previous equation, and we will get the transfer function as Ls upon R plus Ls. So again, here we are considering that the initial condition is 0. That means the current stored in inductor is equal to 0 at time t equal to 0. Now we'll take another example, that is our series RLC circuit. So in this circuit, now we are having two energy storing elements, that is capacitance and the inductor. So we have to understand that what is the input and what is the output. Then only we can calculate the transfer function. So for this example, we have taken the total applied voltage as input and the voltage across the capacitor as output. So the first step is we will apply the KVL. Now the total applied voltage will be equal to voltage across the resistance plus voltage across the inductor plus voltage across the capacitor. And their individual voltages values we can calculate, like voltage across the resistance is equal to R into IT. Voltage across the inductor will be equal to value of inductance multiplied by rate of change of current across the inductor, and the current value is equal to capacitance C multiplied by rate of change of voltage across the capacitor. Now we can replace these currents value in these two previous equation, and we will get VR and VL in terms of voltage across the capacitor. Now we will replace those values in the KVL equation, and we will get the final equation as V in is equal to the function of voltage across the capacitor. Now we can take the Laplace transform of this particular equation and we will get the same relation in Laplace domain, in frequency domain. Now simply we have to take the ratio of Vc divided by V in and we will get the transfer function. So the transfer function that we are getting is L 1 upon LC S square plus RC S plus 1. So here from the previous example, if we compare, in all the previous examples we are having only the one energy storing element, either capacitor or inductor. But in this particular example we are having two energy storing elements, that is the capacitor as well as the inductor. That's why the order of the equation, that means the highest power of S in denominator in the transfer function is 2. So likewise, we can solve further examples and we can estimate the transfer function. So if we summarize, we can say that today we have seen that how to calculate the transfer function for any given electrical circuit consisting R, L and C by applying the basic voltage and current equations. Thank you.